September 26th, 2022. NASA deliberately crashed a spacecraft into an asteroid at 14,000 miles per hour. The world celebrated. We'd proven we could defend Earth from cosmic threats. But then, scientists noticed something terrifying. The debris wasn't behaving normally. Chunks of rock were organizing themselves into clusters, accelerating in ways nobody predicted, and one of those clusters is now on a collision course with Mars. We didn't just move an asteroid, we might have created dozens of new threats, and we have no idea where they're all going. Right now, there are over 30,000 asteroids orbiting near Earth. That's 30,000 potential extinction events circling our planet like vultures. Some pass closer to us than our own moon, others, we don't even see them coming until days before they arrive. February 15th, 2013, Chelyabinsk, Russia. A 60-foot asteroid screamed through the atmosphere and exploded with the force of 30 Hiroshima bombs. No warning, no time to evacuate. The shock wave shattered windows across 6 cities, injured 1,500 people, and sent a message to every space agency on Earth. We are not prepared. That explosion released 500 kilotons of energy from a rock the size of a small yacht. Now imagine something the size of a football field or a mountain. The asteroid that killed the dinosaurs was 6 miles wide. It reset Earth's evolutionary clock in minutes. That level of impact happens roughly once every 100 million years, which sounds comforting until you realize the last one was 66 million years ago. We're overdue. But here's what keeps astronomers up at night. We don't need a dinosaur killer to end civilization. A Chelyabinsk-sized rock hitting a major city would kill millions. A slightly larger one landing in the ocean could trigger tsunamis that devastate entire coastlines. And there are thousands of these rocks out there, many still undiscovered, some with our name on them. This is why NASA launched DART, Double Asteroid Redirection Test. The mission was simple, almost primitive. Take a 1,200-pound spacecraft, accelerate it to 14,000 miles per hour, and slam it into an asteroid to see if we could knock it off course. No nuclear weapons, no explosions, just pure kinetic force. A cosmic punch to see if we could change destiny itself. The target was perfect. Dimorphos, a 5.3 0-foot-wide space rock orbiting a larger asteroid called Dimorphos. The two locked in an orbital dance 7 million miles from Earth. Far enough to be safe, close enough to monitor. If DART could change Dimorphos' orbit around Didymos, we'd prove that humanity could deflect an asteroid heading for Earth. For 10 months, DART traveled through the void. No course corrections needed, just a straight shot toward cosmic history. Ground telescopes tracked every mile. Scientists ran simulations. The world watched. This wasn't just an experiment. This was humanity's first real attempt at planetary defense. The math was elegant. Hit the asteroid hard enough, and you change its velocity by a few millimeters per second. That tiny change, multiplied over millions of miles, becomes the difference between an impact and a miss, between survival and extinction. NASA calculated they needed to shift Dimorphos' orbit by at least 10 minutes. Anything more would be a bonus. September 26th, 2022, 7:14 p.m. Eastern Time. DART's camera transmitted its final images. The surface of Dimorphos filled the screen, growing larger with each frame. Rocks, boulders, a moonlet rushing toward the lens at impossible speed. Impact. The spacecraft disintegrated instantly, converting 11 billion joules of kinetic energy into the most expensive demolition in human history. But it worked, spectacularly. Dimorphos' orbit didn't shift by 10 minutes. It shifted by 33 minutes. NASA had predicted a gentle nudge. They delivered a knockout punch. The asteroid's orbital period around Didymos dropped from 11 hours and 55 minutes to 11 hours and 22 minutes. In orbital mechanics, that's not just significant, that's revolutionary. Dimorphos slowed by 2.7 millimeters per second, exactly the kind of change that, over time and distance, would deflect an Earthbound asteroid into harmless space. Scientists around the world erupted in celebration. We'd done it. We'd proven that kinetic impact works, that we could defend our planet, that extinction wasn't inevitable. Papers were written, awards were planned. Humanity had just leveled up its cosmic defense. And then the debris showed up. 2 million pounds of rock and dust ejected into space. That's 300 elephants worth of material, launched in every direction, creating a debris tail stretching over 6,000 miles. This was expected. What wasn't expected was how that debris behaved. Instead of scattering randomly like shrapnel, the fragments organized themselves into distinct clusters, clumps of rock moving together in formations that looked almost deliberate. Some stretched into long, stringy patterns that defied the chaos of a 14,000 mile per hour collision. This wasn't random. This was structured. Worse, some fragments were moving 3 times faster than predicted, not just drifting away from the impact site, but actively accelerating, as if the collision had triggered secondary explosions that nobody anticipated. One cluster launched at such an angle that it might have given Dimorphos an additional push, essentially hitting the asteroid twice with one impact. Scientists started running new calculations. Where were these fragments going? How fast were they really moving? And most importantly, did we just solve one problem by creating dozens of new ones? The uncomfortable answer started emerging from the data. We might have. One cluster of debris is now on a trajectory toward Mars. It won't arrive for 6,000 years, moving through space at speeds we're still calculating, carrying enough mass to create a meteor shower on the Martian surface. We didn't just move an asteroid, we created artificial meteors and aimed them at another planet. Another cluster could reach Earth's orbit in about 30 years. Not a threat, just a light show. Bonus fireworks courtesy of NASA's planetary defense test. But here's the terrifying, what if this had been a real emergency? What if we deflected an actual Earth-threatening asteroid and accidentally created a dozen smaller threats in the process? What if, in our desperation to save ourselves, we turned one bullet into a shotgun blast? This is the nightmare scenario, keeping planetary defense experts awake, because the math that seems so simple, hit asteroid, change trajectory, turns out to be catastrophically complicated when you account for real-world physics. The asteroid's composition, its rotation, its structural integrity, all of these factors determine not just if you can move it, but what happens when you do. Dimorphos isn't a solid rock. It's what astronomers call a rubble pile, a loose collection of boulders, gravel, and dust held together by nothing more than weak gravity. Less like a bowling ball, more like a sandbag floating in space. When DART hit, it didn't punch through solid material. It hit a cosmic sandcastle. The impact shattered the surface, collapsed internal structures, and sent material flying in unpredictable directions. The loose composition amplified the effect, making the orbital shift larger than expected, but also creating far more debris than models predicted. We got the result we wanted, and a dozen results we didn't. And here's the truly unsettling part. We don't usually know what an asteroid is made of until we hit it. We can make educated guesses based on spectral analysis and radar observations, but we can't know for certain if we're dealing with solid iron, loose rubble, or something in between. Every asteroid is a mystery. Every deflection attempt is a gamble. The European Space Agency is launching Hera in 2024. Its mission, travel to Dimorphos and study the aftermath up close. Measure the NT6 crater. Map the new shape. Calculate exactly how much mass was ejected and how much remained. Determine if Dimorphos is now tumbling through space with a destabilized rotation. Hera will give us the data DART couldn't. It will show us what really happens when you punch an asteroid at full speed. It will help us understand not just if we can deflect space rocks, but how to do it without creating new dangers in the process. Because next time, it might not be a test. Next time, the asteroid might be heading straight for New York, or Tokyo, or Mumbai, and we'll have one shot to get it right. No do-overs, no second chances. Just the knowledge we gain now and the hope that it's enough. The DART mission proved we can change an asteroid's course. Now we need to prove we can do it safely, that we can defend Earth without accidentally creating new threats, that our cure isn't worse than the disease. We're not there yet. But we're learning, and hopefully, we'll we'll learn fast enough. If this video opened your eyes to what's really happening above us, hit that like button and share it with someone who needs to know. Subscribe for more deep dives into the science that's reshaping our future. Because space isn't just beautiful, it's dangerous. And understanding that danger might be what saves us all.